Here we discuss some properties of orthogonal complements. So again, we assume that V is an inner product space with inner product as shown. So note that V in our discussion here is not necessarily Rn with the standard inner product. So first, we note that the orthogonal complement of the set containing the zero vector is the full, the entire vector space V, and conversely, the orthogonal complement of the entire space is the set containing the zero vector or the zero subspace. And the reason for these two properties is that the only vector that is orthogonal with every vector in V is the zero vector. Suppose S is a subset of V. Note that if the zero vector lies in S, then the intersection of S with its orthogonal complement is the zero subspace. Otherwise, meaning if the zero vector is not in S, then S and its orthogonal complement has empty intersection. So they don't have any common elements. And the reason for this, for these statements, is that the only vector that is orthogonal with itself is the zero vector. Next property, if S is a non-empty subset of V, then the orthogonal complement of S is a subspace of V. And this can be shown using the subspace test. Now first, we note that S-perp is non-empty because the zero vector is contained in S-perp. Okay, the zero vector is perpendicular with every vector in S. So next, we show that S-perp is closed under addition of vectors in V. Okay, so suppose X, Y are vectors in the orthogonal complement. So by definition, this means that XV is 0 for all V in S and YV equals 0 for all V in S. Okay, then for any arbitrary vector Z in S, we have the inner product of X plus Y with Z equals the sum of the inner products of X and Z and Y and Z. This is by the third property of an inner product in the definition. But as we assumed that X and Y are in S-perp, the inner product of X and Z is 0 and the inner product of Y and Z is 0. So the inner product of X plus Y and Z is 0 plus 0 or 0. This shows that X plus Y satisfies this condition because Z is arbitrary. So X plus Y Z equals 0 for all Z in S. This tells us that the sum X plus Y is in the orthogonal complement of S. Finally, we show that S-perp is closed under scalar multiplication in V. So suppose X is an element of S-perp and C is a real number, a scalar. We have to show that for any element of S, the inner product of Cx with Z is 0. And indeed, by the fourth property of an inner product, the inner product of Cx Z is equal to the product of the real number C with the real number given by the inner product of X and Z. but x is in S perp and z is in S. So the inner product of x and z is 0. And so this inner product equals c times 0 or 0. This shows that Cx is in S perp, and we conclude that S perp is a subspace of V. Next, suppose we have a subset S of vectors from V, a finite subset, say with elements V1, V2 up to V sub k. Then let's consider the span of S. So the span of S is a subspace of V. Let's denote that span by W. Note that if X is in the orthogonal complement of S, then X belongs to the orthogonal complement of the span of S. Okay. In other words, S perp, okay, the orthogonal complement of S is always contained in the orthogonal complement of the span of S. To verify this, we have to show that every element X in S perp satisfies the condition for W perp. So suppose X is in S perp. This means that X, or rather the inner product of X with every element in S is 0. So X, the inner product of X with V1 is 0. Inner product of X with V2 is 0, and so on. Down to the inner product of X with VK, all 0. That's what this statement means. So we have to show that X is in W perp. Okay? So in other words, we want to show that the inner product of X and Y, this X, with all vectors Y in W is 0. Okay? So this is the definition for elements in W perp. So why is that true? Indeed, if we take an element Y in W, because W is the span of S, Y is a linear combination of elements from S. So we can write Y as R1V1 plus R2V2 and so on down to RKVK, where R1, R2 up to RK are scalars. From this, we see that the inner product of X and Y is the inner product of X with this expression. Okay, so we just replace Y with this linear combination representing Y. So at this point, we apply the properties of an inner product. Okay. So this inner product can be written as a sum of scalar multiples of inner products. Okay, so we apply the distributivity. So it can be written as a sum or as the sum of the inner product of X with R1V1, X with R2V2, up to X with RKVK. But R1 is scalar. So the inner product of X with R1V1 is equal to R1 times the inner product of X with V1. Similarly, the inner product of X with R2V2 is equal to R2 times the inner product of XV2 and so on up to the last term. Okay. So at this point, we apply the note that we wrote earlier from our assumption that X is in S perp. X V1 equals 0. So this guy is 0. X V2 equals 0. This guy is 0 and so on up to the last term. So this is nothing but R1 times 0 plus R2 times 0 and so on up to plus RK times 0. Sum of zeros or 0. And that concludes the proof of this property. Again, this property tells us that a vector that is orthogonal to S is also orthogonal to the span of S. In fact, the reverse inclusion is also true. If a vector is orthogonal to the span of a set of vectors, then it is also orthogonal to the given set. And these two properties combined give us the stronger form. S-perp equals orthogonal complement of the span of S. And this is a nice result because this tells us that in order to determine the orthogonal complement of a subspace of an inner product space, it's enough to find a basis for that subspace and determine the orthogonal complement of that basis. A basis is better because it has finitely many elements. So instead of computing inner products with infinitely many vectors, we can just reduce the problem to the computation of inner products with finitely many vectors.